Hello everybody and welcome to another lecture video in Dynamics. This is Professor Algara with the second part of chapter 16 in Dynamics, like I said. Alright, so we'll be talking about a lot of things, but the most important ones is relative motion analysis, both from the position and velocity perspective. We will also talk about the instantaneous center for velocity, and then we'll finish up with relative motion analysis from the acceleration standpoint. Um, it is important to say that we'll be using everything that we have learned, in the first part of the chapter. And if you haven't watched the video, just go and watch it. It's right here on the channel. All right. So when a body is subjected to general plane motion, it undergoes a combination of translation and rotation. That's what we were studying last week. So we have, time t and times t plus dt. So you have the var, which has 2 points, A and B, and this part it's basically translating into something like this and then rotating into its final position, which is this. That's what this image is telling you. We go from here into this and we try to study this movement into a combination of two, one that involve pure translation and another one that involve rotation. As you can see here, for example, the movement can be divided into this step and then it translates just translating up to this point, and then finally it rotates to point B. What I want you to realize with this is that as we build up the equation, we will be dividing what is, due to translation, what is due to rotation, and what is due to both. All right, so we are trying to build a relative position vector combination as we've been doing since statics. So if you see point A has an initial position at t and then a final position at t plus d plus delta t, and then point B has an initial position here and a final position right here. If you draw a vector from the initial position to the final, you will get a small differential vector of position A, and then if you do the same thing for B, you will have a small differential vector of position for B. What is important here is that you can take this vector and actually translate it down here so you can form, your triangle and then get a relative position vector of B respect to A. And if you have that, as you can see here, you can build the equation that everybody's so used to, in which you have the position of B is equals to the position of A plus the relative position of B respect to A. And this one right here, it's the displacement due to translation and rotation, which is this, right? And then this one right here, these two elements of the equation, it's what we have on the second picture, which is a combination of the translation and the rotation, both at the same time. Okay, the important thing behind this whole slide is that you see the relationship of combining, or analyzing a whole movement into specific parts. So for velocity, it's very similar to what you've been doing until now. So basically, you take your position equation, the one that we developed in the previous slide, and then you derive that respect to time. When you derive it, you will get this equation right here, velocity of B, it's equals to velocity of A plus the relative velocity of B respect to A. What is very important for us to see is that you have an initial bar with 2 points, and this point obviously has an angular velocity, which is what is causing, the rotation part. So you will divide that movement into a translation and a rotation. And if you do that and you write that into the equation, that's how you will get the equation that relates the velocity of both of them. What is very important about these whole equations is that when you are located into this element, right? And now we want to use what we have learned throughout the chapter, you have to realize that as you have your relative velocity of B respect to A, you can get then an equation that will relate the angular velocity and the position vector, or the radius, the distance from the point in which it's pivots to the point where the velocity is located. So that equation is just the equation we developed in the first video of this chapter. Okay, so velocity of B respect to A is not more than the angular velocity of the bar times the distance from the points that are involved in this study. In this case is, the position or the vector position of B respect to A. And that is very important because then you can write the equation in terms of velocity and angular velocity at the same time. This equation right here, when using the relative velocity equation, points A and B should generally be points on the body with a known motion. Often these points are pin connections in linkage. For example, point A, as you can see here, point A on the link AB from here to here must move along a horizontal path, whereas point B move a circular path. As you can see, CB are connected with AB on the pin B, and this is moving from here to here, and that is describing a circular path. As you do that, you can then write your equations for A and B in a single element, right? You can take A and B, and the velocity that you have at B, it's also felt right here on AB. And therefore, you can have a single element with both velocities, as a known value, so you can use the equation to find what is needed, whether it's angular velocity or something like that. So when a wheel rolls, and this is an special case, and it's quite hard to explain it, but anyways, when a wheel rolls without slipping, point A is often selected to be at the point of contact with the ground. Since there's no slipping, point A has a zero velocity. Furthermore, point B at the center of the wheel move along a horizontal path, and therefore BB has a known direction parallel to the surface. So as you are moving right here at this instant, and that's very important that we realize in that instantaneous velocity at that point is zero. That is actually what is causing the wheel to rotate, right? Because since the ground is not moving, right, it's rotating, and at this point at A, it's where it's pivoting, right? So if you see this as a pivot, then that pivot will cause the wheel to rotate because the ground is not moving. And at the same time, BB will have a velocity which is known, and that will be parallel to the path of motion, if you want to see it, or parallel to the surface. So a procedure for an analysis would be, at first we need to establish a fixed x and y coordinate directions and draw a kinematic diagram for the body. Then we need to establish the magnitude and direction of the relative velocity vector b respect to a. Then once we have that established, we will write the equation of bb equals to ba plus bb respect to a in the kinematic diagram. Represent the vectors graphically by showing their magnitudes and directions underneath each term. We have to write the scalar equations from the x and y components of these graphical representations and then solve for unknowns. When we're talking about vectorial analysis, we need to establish at XY coordinate directions and draw the kinematic diagram showing the velocities BA, BB, RBA, and omega. If these magnitudes are unknown, the sense of directions might be assumed, right? So you will assume that it goes to the right or left based on the movement itself and based on what it's given. You will assume things with facts in your hands. Then we need to express the vectors in Cartesian form and substitute them into the equation right here, BB plus BA, I'm sorry, BB is equals to BA plus omega times the position vector of B respect to A. We need to evaluate the cross products and adequate respective I and J components to obtain two scalar equations. So basically, you will have that huge equation with a lot of I and J, and then you will compare I's with I's and J with J, so you can obtain different equations to solve for the unknowns. Then the equations, if the equations yields to a negative answer, then the sense of direction of the vector is opposite to the one that was assumed. So now we're going to do an example based on what we just covered. So we have a crank that rotates OA with an angular velocity of 12 radians per second. We need to find the velocity of piston B and the angular velocity of rod AB. Okay, so notice that a point A move a circular path. The directions of BA is tangent to the path of motion. We can draw a kinematic diagram of rod AB and use the equation. So that would be the plan based on the procedure for analysis that we established previously. So we are given with the angular velocity of OA, and as we can see, the whole point with this is that we can find um, a common member, and we can study just that member by using that particular equation. So we see that this bar it's moving into a circular path, and therefore you can easily assume that BA will be given into that direction, and if we move to the left, then B should be then moving like this. And if we study, a vector that goes to from A to B, that should be our vector given, which is R B respect to A. And we have a length for the var, and we can easily form a triangle as you can see here. All right, so important facts about this. We can find omega AB because we don't have the velocity yet, but we have, the angular velocity, and we have the distance from O to A. With those two, we can easily find velocity A. And when then you transfer that into the element, we can start using an equation, this equation right here, in terms of vectors in order to find what is needed. So how so? So let's just first build this into a picture that we can all understand. So we have this guy that it's OA, right? OA, and this one has a velocity that we will call VA. It's supposed to be perfectly horizontal. Then we have the vector right here that is called R with respect to A, and then on this point we have perfectly vertically. Sorry for my very poor drawing skills. We have velocity in B, and we also have an angular velocity of 12 radians per second. Okay, so with that being said, we know that the equation we're looking for is BB. It's equals to BA plus omega AB times or cross product of R B respect to A. All right. So we we don't know. We have this unknown, we have this unknown too, and we don't know this one either. So let's just start working with what we have. I can easily find VA because I know that VA it's equals to omega OA, right? That multiplies the distance from O to A. And I can easily find this because it's perfectly horizontal. So I can use the scalar form, and that will be equals to 0.3 that multiplies the angular velocity, which is 12. And this is going into the I direction, or minus I, sorry. If I do this calculation, then I will get that this velocity A is minus 3.6 I meters per second. All right. So now that I have that value, it's easier for me to start playing because I know this. This is perfectly given, and I know the direction of BB, right? If I know the direction of BB, which is going to the J, then I can start writing the equation as follow. So BBJ, it's equals to BA, which is minus 3.6 in the I direction. And then this is plus omega AB, which remember always go into the k direction, that multiplies this as a vector. And right here, if we go back to this, we have a triangle that is formed as 0.3 right here, then this is 0.6, and with the cosine of 30 we can find how much we have right there. So we can start building that particular one, but I will not get into that. I will just put into the values right on. So it's 0.6 that multiplies the cosine of 30 into the I direction minus 0.6, that multiplies the sine of 30 into the j direction. And what is important here is that you have to apply cross product for each one of them. So which means you need to do the cross product of k, cross product of I, k, cross product of minus j. And that's very important that you keep track of that, because if you don't, then you will get, an answer that you're not looking for. Minus 3.6 in the I direction, and then the first item will be plus 0.5196 omega AB in the J direction, plus 0.3 omega AB in the I direction. So the only thing that is left for me to do is compare i's with i's and j with j, so we can get an equation for each one of the components. So for I will get 0 because there's no I right here on the equation. So 0, it's equals to minus 3.6, which is this, plus 0.3 omega AB, which is this right here. And that's 1. From here, I can get that omega AB, it's equals to 12 radians per second. So I got my first one, and now with the J's, I will get that, BB, which is here, right here, this one. It's equals to 0.5196 omega AV, which is this, and I already have omega AV, so I can plug that into the equation, and solving for VV, I will get the VV, it's equal to 6.24 meters per second. Okay, and that's about it. So you just, and I want to move into the next one because I put that into this. What you did at first, and that was critical, was to establish a direction for each one of your unknowns so you can start playing with the equation. So if we go back into this, you will realize that that was critical, because then I knew the direction of my VA. I already knew the direction of omega, and I assumed the direction of BB based on all of the connections given. And with that, I was able to solve the exercise very easily. All right, so now we'll be talking about something very important. It's instantaneous center of zero velocity. This is very important, and the reason why is because there is always a point of any element that will help you simplify your equation, your relative velocity equation. For anybody undergoing planar motion, there always exists a point in the plane of motion at which the velocity is instantaneously zero. This point is called the instantaneous center of zero velocity. It may or may not lie on the body. If the location of this point can be determined, or that you can easily calculate, then the velocity analysis can be simplified because the body appears to rotate about this point at any instance. And when that happens, you're just simplifying your relative velocity equation into something a lot simpler. So to locate, so we have different cases, right? So the first one is when velocity of point B, or point A, sorry, on the body and the angular velocity of the body are known. When that's the case, right, as you can see right here, and concentrate on the picture, your omega is known and also the velocity. So the theory tells you that your IC, or your position vector, will be perfectly perpendicular to VA. So you will just draw a line that is perfectly perpendicular to this somewhere that you don't know. And that position vector is RAIC, okay, or the distance from the point A to your instantaneous center. And you can easily get that because you know from theory that velocity at any point is equals to omega times the radius. And if you are given with this and this, then you can just solve for RAIC and find that distance by dividing VA over omega. And if you do that, then you can get how much longer it's from here, or how much long is from here to this point, and therefore everything will be specified. And why is that important? Because that's the thing, right? So if you try to write an equation that will relate point A to your instantaneous center, right? And we want to write that equation, we will know that, for example, VA will be equals to the velocity at the instantaneous center plus the velocity relatively, right? A over IC. This one, the theory tells you that is zero, and now your equation becomes a lot simpler because VA will be equals to the velocity of AIC, and you can get that if you have information such as the one I just explained. Okay, so this method is very useful when working with dynamics problems because you can simplify your problem into something more manageable, okay, something that you can easily work with. We have a second case in which we have the body, and the body has 2 points, let's say a bar like the one you had before. If your two velocities are known, then you can draw a line perpendicular to each one of those velocities as you can see here. And then where they both intersect, that will be your instantaneous center. And the same equations can be applied as we did before. Okay, remember that this method is used for you to simplify your calculations. Okay, so if you have 2 points known in your body, like A and B, and then you know they're non-parallel, then you can easily find the instantaneous center of velocity by just drawing a line perpendicular to each one of those velocities where they intersect. That will be the point you're looking for, and therefore you can make the velocity at that point equals zero, as you can see here. And a third case is when the magnitude and direction of two parallel velocities are known. Here, the location of IC is determined by proportional triangles. So, just as before, if we know the magnitude and direction of two parallel velocities, as you can see here, A and B, then I can start forming different triangles and find the location and all the information needed so I can use that method in order to find, values of omega and things like that. All right, now we'll be solving an exercise based on everything that we've been covering so far. So a linkage on undergoing motion as shown, right here. The velocity of the block BD is given, which is 3 meters per second, and we need to find the angular velocities of links AB, which is from here to here, and then BD from here to here. We need to locate, so the plan would be to locate the instantaneous center of velocity, of zero velocity of link BD, and then solve for the angular velocities. So why is this so important? Well, guys, like I said, we need to isolate everything into one single element so we can work it in a better way. So if you see A, B is rotated with this, you can see here like the probable movement. So if that's the case, you already know that it's moving with a circular pattern and therefore the velocity in B will have this direction. And you can see here that actually D is moving into this direction, so BB will actually be the opposite. It will go like this. It will go like that. And then if we isolate this, right, we can easily then draw a line perpendicular to BB and another perpendicular to this, and we can find the IC point. And from this point, then we can use the equation of relative motion in order to find what's been asked of us. Let me just move to this. In the solution, since D moved to the right, it causes the link AB to rotate clockwise about point A. The instantaneous center of velocity BD is located at the intersection of the line segments drawn perpendicular to BB and BD. Note that BB is perpendicular to the link AB, therefore we can say that IC is located along the extension of AB. This is just what I just explained it to you. So we have, velocity right here, perpendicular to that velocity, we draw a line, and then we have BD, which is giving. If you draw a line from here, then you will have the point you're looking for, which is IC. And I just want to go ahead and do that in a diagram. So we have this that we will call B and D, and we have a velocity here that is given, and this one is 3 meters per second. We also have a velocity on B right here. That is something we don't know, right? Until now, we don't know that because we don't have angular velocities. So we will go ahead and perpendicularly build a triangle. And this right here, it's IC. So this vector is called RVIC. And this one right here is the vector RBIC. Okay, because remember, we're playing with everything that we have. There is a 45-degree angle right here, and we have the length of this guy, which is 0.4. Okay, what else do we know? We don't know anything else. So now we just need to work with what we have. And if we have the 45-degree angles and we have 0.4, we can easily find these two. And that's what we'll do first. So RB IC will be equals to 0.4 that multiplies the tangent of 45, and that gives us a value of 0.4 meters. For R the IC, what we'll do, we'll use the cosine of 45, which is equals to 0.54, sorry, over R the IC. If I solve, for RDIC, I will get that RDIC it's equals to 0.56 meters. Okay, and why is this very important? Because now that you have that at D, right, you can easily find your omega D, your omega BD. How do we find that? Well, easily. The velocity md it's equals to that omega BD that is multiplied by the distance of D from IC. You already have this, and this is what you're looking for, and you already have this because you just calculated right here. If we solve this equation for omega BD, we will be able to find what we're looking for. This is radians per second. So we will get that omega BD is equals to 5.3 radians per second. So now that I have this, I can use this omega into a new equation that will relate BB and omega BD. How so? Well, you know that velocity in B will be equals to the same omega BD that it's also multiplied by the distance from BIC, which is the one you just calculated, right? So velocity in B will be equals to 5.3, which is what we just calculated, that multiplies 0.4, and that will give you a value of 2.12 meters per second, right? And that's the velocity. So now that I have that, all I have to do is to plug velocity into the bar. So I will just go back to the exercise, and if I have velocity in B, which I just calculated, and you have this, you can find omega, right? Because remember, velocity in B, it's equals to omega AB that multiplies that distance of AB. Okay? And that's what I'll do. I will take that value and plug into a new equation, right? So BB it's equals to omega AB times the distance AB. Okay, and I already have BB, so I will basically solve omega AB as BB over RAB. This is 2.12 over the distance, which it's 0.4, and that will give me omega AB, which is 5.3 radians per second. And with that, I just solved the exercise. Guys, what I want you to realize is that what we do when we have an exercise, and this is very similar to what we had in the strength of materials, right? You have to break this up and start translating information from one bar to another, right? We found a common point on B, and then we found the IC of the bar BD because that's what was given. With that, I found omega of this bar, then with the omega of this bar and this distance, I was able to find BB, and then I built another equation from coming from this side, and I was able to find the other omega that was requested of us. And now we will talk about acceleration, relative motion analysis from the acceleration standpoint. So very similar to what we've been doing, acceleration can be obtained by deriving the velocity equation respect to time. Okay, this equation relating the accelerations of 2 points on a body is determined by differentiating the velocity equation with respect to time, as I just said. So you will have three elements, this one, then that one, and this one. So these two correspond to the absolute accelerations of point A and B in their measure from a set of fixed axes A and X and Y. So when it comes to this one, which is what we are more focused on, we will divide this into tangential and normal components. Relative accelerations into tangential and normal component, and it's just the exact same thing that we've been working from day one when we talked about acceleration, in terms of tangential and normal components. So if we divide this as we did it before, we have, a general plane motion in which accelerations are specified and also omega and alpha, right? We can divide that into translation and rotation. And the rotation about a base point is divided into the relative accelerations of v respect to a. And for that, we will have a component in the tangential one and a normal one. The normal their normal one will have an equation that is already set, which is equals to negative omega square that multiplies the distance of v respect to a, and that's in the normal direction, and it's negative because it's pointing towards the negative side of the vector that forms v respect to a. And then we have the other equation, which is the tangential acceleration, and that equation is given, we calculated in the previous part of the chapter, which is alpha that multiplies the distance of our VA. It's very similar, or you can see an analogy when we talk about angular velocity. Okay, so what we do, right? We keep the absolute values, and then we take, the equation for acceleration, the tangential one, which is alpha, cross product of the vector RBA, and then we add the equation for the normal component of the acceleration, which is minus omega to the square that multiplies RV respect to A. And we have to realize that this is an scalar product where this one is the cross product because it's a vectorial form. All right. Since the relative acceleration components can be expressed in tangential and normal, based on the equations that we already calculated before, then now the general equation becomes like this. And this one, guys, can be used for anything, any of the problems that will be using relative movement from the acceleration standpoint. As I said before, as a reminder, the last term in the relative acceleration equation is not a cross product. It is the product of an scalar. In this case, is the square of the magnitude of angular velocity and the relative position. Okay, just keep that in mind. If we have to establish a procedure for analysis, it's very similar to what we had before. We need to establish a fixed coordinate system, then we need to draw the kinematic diagram of the body, then we have to indicate absolute accelerations, then omega, alpha, and obviously the position vector, the v of v respect to a. If the points A and B move along a curved path, then their acceleration should be indicated in terms of the tangential and normal, as you know, that's what we said. And then we will build the equation, the general equation, and then we will apply that equation to the problem. Then obviously, if that equation yields to a negative answer of an unknown magnitude, it indicates that the sense of direction of the vector is opposite to the one that was shown on the diagram. And now we'll be solving a quick exercise, so we can actually put in use what we have learned. But this is just a combination of everything that we've been doing ever since we started chapter 16. But anyways, you have point A on a rod AB, as you can see here, and it has an acceleration of 5 meters per second square, and then also a velocity of 6 meters per second at point A, which is right here. Then they're asking us to find the angular acceleration of the rod and the acceleration at B at this instant. So if you look at it, and I wanted to leave this solution right here, we should follow the problem solving procedure. So we have first to assign, your X, Y, and Z, and then after that, you need to pretty much utilize everything that you know until now so you can find values. So you can see here that the omega of the bar can be easily found because you have the velocity at one point, and if you have that velocity which is known and also know the direction of BB, in this case could be this or maybe to the other side, but it doesn't matter because you will just draw a line perpendicular to that velocity which will take you into this, and if you do the same thing for velocity at A, that will tell you exactly where the IC point is, and if you know the distance from this point to this point, then you should be able to find omega, and that distance is easily can be easily calculated because you have 5 from here, 4 from here, which means that from here will be 3. So if you take the equation that you can see here, omega is equals to be A divided by the distance from A to IC, which is 3, that will tell you the omega of the bar. And that will simplify your equations a lot because now you have another thing that you can use for this. So now what you need to do is to start assigning everything in terms of, as a vectorial form because you don't know, the value of A, but you know the direction, and based on that, and also the fact that you are giving the acceleration with both direction and value, then you can start establishing your equation with the general equation of relative movement for acceleration, which is, AB, it's equals to AA plus alpha that multiplies the vector of B respect to A and minus omega, and this is a cross product, don't forget that, and omega square that also multiplies the vector B respect to A. This one is an scalar multiplication and this one is a cross product, right? So what I need to do is start plugging into the values. So acceleration in B, which is what you're looking for. They're telling you the direction of B. In this case, I will say that AB is going to the I direction, and then AA is giving us a negative value 5J, right? And that comes from this one plus alpha, which you don't know, but you know that it's in the K direction, cross product of your vector R, this one right here, and that vector will be equals to 3I minus 4J, and this is minus omega to the square, which is 2 to the square, that multiplies the same vector, which is 3I minus 4J. And don't forget, I've said it so many times, but this is an scalar multiplication, and this one is a cross product. So if I keep solving this, I will get that ABI, it's equals to minus 5J, and then I perform the cross product. In this case would be plus 4 alpha I. And if I solve this a little bit further, I will get that ABI, it's equals to 4 alpha minus 12 I plus 3 alpha plus 11 J. And what I need to do is solve for alpha and AB by comparing I's and J's, right? So the first one I have I's, and this one will be AB, which is this. It's equals to 4 alpha minus 12. And then if I do the same thing for J, I will get 0. It's equals to 3 alpha plus 11. And I will solve these two, and I will get that AB, it's equals to minus 26.7 meters per second square, and then alpha it's equals to minus 3.67 radians per second square. All right. So if you see here, I just put in place everything that we have learned until now in order to get the calculations as I needed it. With that, we have concluded chapter 16 in the book. As I told you, one of the toughest chapters, but also it's just giving you more information that you can use to solve your exercises. I always see dynamics as a big puzzle, and I'm just giving you the pieces so you can solve the puzzle. All right. So if you have any questions, please email me, and if you don't, I will see you in the next video. Thank you so much for watching.